Okay, so welcome back. Let me find my sheets from last time since I had some definitions that I needed to finish up on. Um, so we had the definition of a region being vertically, horizontally, or just simple, right? So this is our list of definitions for a region being vertically simple, horizontally simple, or just simple. Some of the examples that we had a look at were the following. So it'll take some practice to get used to identifying a region as vertically or horizontally simple, or both. And also, more than just identifying it, you're actually going to have to find these functions. So that's the other thing. Actually finding the specific functions that allows you to show that these regions are vertically or horizontally simple is also something that's going to take some practice. In fact, in this course, in doing the integrals, at least at first, most of the work that you do is going to be in dealing with the region itself. And I mean, that's true actually for most of these multiple integrals that you're going to be doing, because as I mentioned previously, the actual integration itself is going to be pretty easy compared to what you've done in your past calculus classes. So the Jack, my email, is it really not on Elms? Here's one. Also, if you email the one that's at math.umd.edu, that's that works too. That doesn't exist anymore. The math.umd.edu address technically doesn't exist, but it gets forwarded to me anyway. So yeah, even as we get further into chapter 14 stuff, which is going to be all of the integration stuff we're going to be doing, it's still going to be most of the challenge in these problems is going to be dealing with the region itself rather than the actual integration, because the integration itself is going to be fairly easy. Okay, so the idea here is that writing this region as a vertically or horizontally simple region is going to be exactly the thing that allows us to compute this double integral. Why do we want to compute the double integral? This is the thing that tells us that volume that we want to compute, right? So the volume bounded, or the volume of the region bounded above by the graph of the function and below by the xy plane on that region R, right? So if R is vertically simple, and the way that we're going to write that is our region is able to be described as the region, right, where the y value is bounded above and below by the functions g sub 1, g sub 2, and this is on the interval ab. Okay, so if that's the case, then we can compute this double integral as an inner integral, where the lower and upper bounds of integration, respectively, are those lower and upper functions that bound y. And then after we have computed this integral, the result is going to be some function of x. We then integrate that function with respect to x on the interval a to b, okay, which is just at both steps. Both of these integrals we're doing are really just like Calc 1 or Calc 2 integrals. And we do this by integrating with respect to each variable in turn, right? So we take turns here, treating the other variable as constant, okay, in this first integral. Okay, and so the second part of this definition, if R is horizontally simple, then we don't have an upper and lower function anymore. We have a left and right function. So the way that we think about R being described is R is a region whose x values are bounded on the left and on the right by two functions of y, so h sub 1 of y and h sub 2 of y, and this is on some interval CD. Okay, so when a region is horizontally simple, this is how we describe it. Okay, so if that's our description of R, then the double integral over R of f of x, y, dA. Again, remember this computes that volume that we're interested in. This is the integral from C to D of the integral from h sub 1 of y to h sub 2 of y f of xy dx dy. Okay. So what's going on here is I'm doing this integral with respect to x first. Okay. Right. Now, this is going to be a little bit unlike what you're used to so far when it comes to questions of does it matter like what order you do these in. Well, you should be able to kind of guess just from how this is stated that it should actually matter. Okay, in general. But in a very special case, you can do these in either order. However, note that it's not as simple as just swapping the order because you have to come up with a description for R being vertically or horizontally simple. What do I mean? I mean, even if R is both, right? If R is simple, then you have a description here of R as a vertically simple region. But that's not the same as a description of R as a horizontally simple region. So you would have to find that if you didn't already have it before you could swap the order. So we're going to see some examples of swapping the order here. But if R is simple, I can do either of these. And the result is the same. But this is something that I can only do if R is simple. Okay. So if R is not simple, I can't do this. Okay, this is going to be called swapping the order of integration here, and it's a special thing. It can only be done on certain regions. Okay, and that makes sense because we saw examples of regions that were vertically simple but not horizontally simple and vice versa. So it would make sense, right, if you could do both in such a case. Okay. Yeah, Daniel. So the C and D is just that you're not guaranteed, even for a region R that is both vertically and horizontally simple, you're not guaranteed, of course, that the bounds on X would be the same as the bounds on Y, right? Even for the most simple regions, right? You're never guaranteed that. Okay. Okay, so let's see some examples on how to do this for the very, very easiest stuff, right? So what's kind of the most basic example? Well, for in Calc 1, we were always integrating over an interval, right? So what is kind of like the most basic region R that we could integrate over doing these things? So the thing that is kind of like the two-dimensional analog of an interval is a rectangle. Right, so let's do the following example. Let R be the rectangle, or, well, it's not just the rectangle itself, right? It's a rectangle and everything inside it. So let R be the rectangular region bounded by the lines x equals -1, x equals 2, y equals 0, and y equals 2. Okay. And I want to find the double integral over R of x² y dA. so let's draw my region. Okay, so what are my lines? My line's x equals -1, so there it is. There's the line x equals -1. X equals 2. That's what that looks like. Right. Y equals 0. Well, y equals 0 is... Oh, sorry. What am I doing? Sorry, I was drawing in the line y equals 2 here. X equals 2 looks like this. And y equals 0 is the x-axis. So the rectangular region out of that looks like that. It's a pretty bad rectangle, but there it is. So there's my region R. Okay. So immediately you see that this region is simple, and so I can describe it as vertically simple or horizontally simple. Let's describe it as a vertically simple region. So describing it as a vertically simple region, I need functions that bound y on some interval that bounds x. Well, what's my functions that bound y? Well, this lower function that bounds y is the constant function 0. And the upper function that bounds y is the constant function 2. Right, and x is bounded by the interval -1 to 2. So this is my description of R as a vertically simple region. Describing it as a horizontally simple region would just be me literally writing those in a different order, right? Okay. Of course, as regions are more complicated and these are actual functions and not just constants, then it's a little bit more involved to actually write a vertically simple region as a horizontally simple region if it's actually simple. But in this case, since everything involved, all these functions are just constant functions, it's a lot easier. Okay. All right, so now I want to compute this. So what do I do? Well, this double integral over the region R of x squared y dA is, just by my definition, this is the integral from -1 to 2 of the integral from 0 to 2 x squared y dy dx. Okay. So what this means is that I do this integration with respect to y first, right? So I do this integration with respect to y, and I treat this, I treat x as a constant, right? And so what is the integral of the expression x squared y with respect to y? So this outer integral I haven't done yet. I'm doing this inner integral right now. So what is the integral of x squared y with respect to y? Well, I'm just treating this like a constant. So, right, so I treat anything involving the other variables constant. So this is just like constant times y. The integral of that is constant times y squared over 2. Right, so this is 1/2 x squared y squared evaluated from 0 to 2 dx. Okay. So now I have an expression in y, or in both x and y, and I'm evaluating that in the y from 0 to 2. Okay, so I'm going to write all of this stuff out. As you get a lot of practice with this, you'll look at terms that have expressions that, if I'm plugging in 0 here, I'm going to get a 0 clearly, but I'm going to write all this out anyway. So this is the integral from -1 to 2 of 1/2 x squared 2 squared minus 1/2 x squared 0 squared. Right. dx. Okay. So then what I get out of this is 1/2 x squared. 2 squared is 4, so 4 over 2 is 2. So I get 2 times the integral from -1 to 2 of x squared dx. Now, at this step, notice that I have a function of a single variable, x, and I'm taking the integral with respect to that, and the limits of integration are constants. Okay, now, of course, the limits of integration for my inner integral were also constants, but that's just because this is a very easy example. In general, though, at this step, when you finish the inner integral, what is left should always be a Calc 1 or Calc 2 style integral. If that's not the case, then you've done something wrong. So at this point, right, there can't be any other variable showing up. Okay. So remember, all of these multiple integrals that you're doing, the answer, right, when you're done, you should get a number. Right, so you should get some real number as your answer when you're finished with this. Okay, and so what do I get here? This is 2 times, what do I get when I integrate x squared dx? Well, I get x cubed over 3. So I get x cubed over 3 evaluated from -1 to 2. And so what do I get? I get 2/3 times 2 cubed minus 1 cubed. Okay, so 2 cubed is 8 minus 1, so that's 9. So this is 2/3 times 9. Which is 6. Okay. Now, what does this quantity show me, right? What does this number 6 mean here? Well, what I was computing is this thing. Another way of phrasing this problem would be consider the region R, right? And consider over this region R the graph of the function x squared y, or z is equal to x squared y. Okay, so over this region R, that function, the graph of that function lives, right? It hovers over this region R. What does this compute? This computes the volume of the region bounded above by that graph and below by the xy plane over this region R. Okay, so this is some kind of weird prism-like thing where the top of it is the whatever the graph of x squared y looks like. Okay. So that's the deal. So this could have been, this problem could have been phrased in a different way. I could have phrased this as a finding the volume problem. Okay. All right, so this is the absolute simplest example that you can come up with for multiple integrals. Let's do more. Note, again, trivially, maybe I'll go back real quick. I could have done this in either order. So you can check if you want to what would happen if you swapped the order of integration here. So the reason why we can easily swap it here is everything involves just a constant, so there's no extra stuff that is needed to rewrite this region. It's as simple as just literally swapping the order that I wrote these in, right? And so doing this in the other way is something that I can easily do, and you'll see that you get the exact same thing. Okay. But let's pick a different region and a different integral that we want to do. So let's evaluate the integral, the double integral over R of 4 minus y dA, where R is the triangular region, well, let's just draw it here. So so this is the triangular region where the left bound of the triangle is from the line x equals -2. The bottom of the triangle is the x-axis, and the bounding line here is the line y equals 1 minus x. Okay, so that this is 1. Okay, so here's my triangular region R. Okay. All right. So, what kind of region is R? Well, R is a simple region, so it's actually both vertically and horizontally simple again. I'm going to treat it as vertically simple first, and then I'm going to at least rewrite it as a horizontally simple region. I may not fully do that integral, but I'm going to show you at least how it was, or how it would be done. Okay, so I want to describe this as a vertically simple region. So in order to do that, what are my bounding functions on y? So the lower function on y is 0, right? And the upper function on y is 1 minus x. Okay, the interval on which these bounding functions live for this region is x, bounded below by -2 and above by 1. Okay. So this is my description of R as a vertically simple region. Can I explain why it's simple? Yeah, so it is vertically simple because I have top function, bottom function, and x is bounded from -2 to 1. But also, I could view this as left function of y, right? It's not a function of x, but left function of y, right function of y, and y is bounded by, or between 0 and whatever that point is, right? Or rather, whatever the y value of that point is. Okay. All right. So that's why this is also horizontally simple. We're going to do this as a vertically simple region first, and then I will go back and write this as a horizontally simple region. Okay. So, maybe I can go ahead and do that, right? So let's write it as a horizontally simple region. So this is written as a vertically simple region. What if I wanted to describe the exact same region R as a horizontally simple region? So I need to find bounding functions on x and then an interval that y lives between to describe this region. So what are my bounding functions on x? I have my left function, which is the function of y, right? That is just the constant function -2. Okay, so remember, right, a vertical line is not a function of x, but it is a function of y. Okay. All right, and then I have a right function. Now, I have it written as a function of x, so I need to find this as a function of y. How would I do that? Well, you remember how to find inverses. Inverse functions, that is, right? Yeah, exactly. So this, Kaylee, this particular example is really easy, right? Because I can just, so it's 1 minus y instead. Because it's just a linear thing, solving for this as a function of y is pretty simple because I can just say, oh, well, if I subtract 1 from both sides, right, I get y minus 1. And then I'd have minus x is equal to y minus 1. So multiplying both sides by -1. I could also write this as x. This is the function x is equal to 1 minus y. Okay. All right. Okay. So, in this particular example, we literally could just swap the letters for x and y. That's not, of course, what you're going to be able to do in general, right? That's it's not going to be that easy. But in this particular case, it works out that way, right? So my left function is x equals minus 2. My right function is 1 minus y. And y is bounded by what? Y goes from 0 to... So y goes from 0 to this height. What is that height? Well, that is the intersection of this line with the vertical line x equals minus 2. So what height is that? It's height 3, right? So this goes from 0 to 3. And this is the description of R as a horizontally simple region. Okay. It takes a lot of practice to get used to writing, regions in both ways. When you can, right? Some regions, of course, can only be written in one way. Okay, but this is a simple region, so we can write it in both ways. And now I can use either of these and the corresponding definition to compute this integral. Okay, I'm going to use the vertically simple one again, but I encourage you to work through this using the horizontally simple one, and who knows, maybe I'll do it here in a second anyway. So I want to compute this integral. So what is this? This is equal to the integral from minus 2 to 1 of the integral from 0 to 1 minus x of 4 minus y dy dx. Okay. All right. So we're doing the inner integral first. So this outer integral is untouched. And the inner integral, this is the integral of 4 minus y dy. Right? So I can do that term by term. All my integration rules that I'm used to for Calc 1 and Calc 2 apply here, right? Because these are actually just Calc 1 and Calc 2 integrals. We're just doing them separately, right? And we're doing two of them back to back. The only thing that's different here, really, is the fact that we're treating, the other variable as a constant. Here, x doesn't even show up, though, right? So what is the integral of 4 dy? Well, that's 4y. What's the integral of minus y dy? That's, minus 1/2 y squared, right? And I'm evaluating this expression in y from 0 to 1 minus x. And then at the end of the day, I will integrate that with respect to x. Okay. So again, this is a polynomial thing, and every term in this polynomial thing involves a y, which means evaluating at 0 is going to mean me plugging in 0 into multiple terms, so I'm not going to get anything from that, but I'm going to write it out at this point. Later we will ignore that, but I'm going to write it out just so that you see how this works. We're not always going to be so lucky as to have a lot of 0 bounds, right? So it's the integral from minus 2 to 1 of 4 times, so I'm plugging 1 minus x into y here. So this is 4 times 1 minus x minus 1/2 times 1 minus x squared. Okay. Minus 4 times 0 minus 1, or I'll write it like this. Minus 4 times 0 minus 1/2 0 squared. Okay. And there's a dy that's there that I ran out of room for. Or sorry, not a dy, a dx. Okay, so that's 0. And so now I just need to clean up this mess. So I'm going to factor out a 1 minus x here. So what is this? Or I could just go ahead and, whichever way you want to do this. You can either factor out an x and then later multiply it out, or you can just expand all this and simplify. So this is the integral from minus 2 to 1 of actually, I am going to factor out the 1 minus x. So this is 1 minus x times 4 minus 1 half times 1 minus x, right? So minus, say, 1 half plus 1 half x. Yeah, that's right. Dx. Okay. All right. And so, what do I get here if I expand this? This is the integral from minus 2 to 1 of the expression I get. So 4 minus 1 half, that's 7 halves. Right, so this is, I can pull a 1 half out, I guess, and turn this into 7 plus x, and do it that way. Do I want to do that? Yeah, I'll do that. So this is 1 half times 1 minus x times 7 plus x dx. So this is 1 half times the integral from minus 2 to 1 of 7. So this would be minus 7x plus x. This is minus 6. Yeah, minus 6x minus x squared dx. Okay. All right. So, I want to leave this on the page, kind of. There we go. So, leaving that kind of on the page. This is equal to 1 half times, and now I'm going to integrate this thing term by term here. So, this is 1 half times 7x minus, so the integral of 6x dx is minus 6x squared over 2, so this is minus 3x squared, minus 1/3 x cubed, and this is evaluated from minus 2 to 1. Okay, so let's do this evaluation. We don't have any zero niceness here, and so we have to actually do this all the way. So this is 1 half times 7 times 1 minus 3 times 1 squared minus 1/3 times 1 cubed, right, minus 7 times minus 2 minus 3 times minus 2 squared minus 1/3 times minus 2 cubed. Okay. Now, if you were doing this like in person, right, if you were worried about time on an exam or something, once you get to this stage where you have totally done both integrals and all that's left to do is this evaluation, this last evaluation is not super duper important in terms of the scope of the problem. Like, 90 to 95% of the credit on the problem is for everything that is leading up to here. This last evaluation can, cause you to have to do a bunch of annoying arithmetic, and while obviously you have to do that in order to actually get the right answer, this last bit is not that important compared to the rest of the problem. So it's everything else that's more important when it comes to that. Okay, so this is 1 half times a big thing here. Let's see. So this is 7 minus 3 minus 1/3 minus 14. So that's plus 14. Here this would be minus 3 times 4. So that's minus 12. So this would be plus 12. And then this last one is minus 2 cubed, so that's minus 8 times minus 1/3 is plus 8/3 minus, so this is minus 8/3. Okay, so let's track through this. This is 7 minus 3 is 4, plus 14 is 18, plus 12 is 30. Right, so this is 1/2 times 30 minus 1/3 minus 8/3 is minus 9/3. That's 30 minus 3, so this is 27/2. Okay. Okay, so we're done here. Now let's see what things happened in this problem. So one, again, we're computing this double integral here. Okay, so we're computing this double integral. Another way I could have framed this, rather than just saying evaluate blah, right, evaluate this double integral, I could have said, consider the function z equals 4 minus y, right? That describes a plane in space. And you could say, consider the region, right, bounded above by that plane and below by the region R in the xy plane, right? So that forms a solid region in space. Compute the volume of that solid region. Okay, well, in order to compute that volume, you would have to evaluate this integral. So that's exactly what this integral tells you. It tells you the volume of the solid region in space, bounded below by this triangular region in the xy plane, and above by the graph of that plane, z equals 4 minus y. Okay. All right. So, more. Let's see, do we have time? Now, if I had wanted, I could have done this exact same computation using the other description of R as a horizontally simple region. So I'm going to set it up, but I'm not actually going to do it. So we could have also done the double integral over R of 4 minus y dA, setting that up as a horizontally simple region here using this. Let me put this back on screen. So here's the region I'm using. So I'm going to do this as the outer integral is going to be the integral from 0 to 3. The inner integral is going to be the integral from minus 2 to 1 minus y of 4 minus y dx dy. Right. And if you want, for practice, you can do that and see that you should get the exact same answer, 27/2. Okay. Now you might ask me, does it matter what order I do it in, right? Could it possibly be easier to do it in one direction than another? The answer is yes. In fact, there's actually some extreme examples where you have integrals that can't really be done without swapping the order. Okay. Do I have time to do... I don't have time to do a really good example that I'll do at the beginning of class next time. And since I don't have enough time to do that, maybe I will go through this just to do it. Actually, no, I have enough time to do the example I want to do. I don't have to wait. So next example. This one's going to be a little bit more involved because this isn't the best way of doing it, but we won't see that until next section. So find the volume of the solid region D bounded above by the paraboloid z is equal to 4 minus x squared minus y squared, and below by the xy plane. Now, this is your first example of one of these double integration problems where you're not explicitly given what R is. Okay, meaning you have to find it from the problem description. Okay, and so how do I do that? What does this paraboloid 4 minus x squared minus y squared look like, right? Well, it looks basically like I've taken the parabola 4 minus x squared in the yz plane, or 4 minus, or sorry, in the in the yz plane, or 4 minus y squared in the other coordinate plane, and rotated it spun it about the z-axis here. So you know what this thing looks like. It looks like this. Now, what about its intersection with the xy plane? What does that look like? So again, we actually did a very similar example to this when we were first talking about representing these types of objects in space. And so this is the picture. I did a bad job drawing this here, but this is what the picture looks like. Okay, so the upper part is this paraboloid, 4 minus x squared minus y squared. Okay, the lower part is the xy plane, but what is that region? So what is this region here? So the intersection of 4 minus x squared minus y squared with the xy plane, how can I see that algebraically? Well, algebraically I can see, oh, this is just me seeing what happens at the level z equals 0, right? Well, at z equals 0, I have 0 is equal to 4 minus x squared minus y squared, so x squared plus y squared is equal to 4. What is that telling me? What is this curve that I just highlighted here? Well, that's a circle of radius 2. Technically, it's an ellipse, Kaylee. And I mean, when we look at elliptical paraboloids, that's exactly what's going to happen here. You're going to get something that's elliptical here. In this case, it's actually just a circle. It's just a circle of radius 2 here, right? And so this region R that I get is a closed circular disk of radius 2. Okay. So this is, again, the best way of thinking about this region R, right? So you weren't given this R. You had to find this from the problem. So the best way of thinking about this region R is I'm shining a light from the positive z-axis direction. I'm shining a flashlight. R is the shadow that this region casts on the xy plane, right? And so there it is. So R is this closed circular disk of radius 2. Now I need to describe that closed circular disk of radius 2. Of course, closed circular disk of radius 2, the easiest way of writing it is it's just the region. It's all x and y such that x squared plus y squared is less than or equal to 4. Right? That's how you describe the closed circular disk of radius 2. All right? But I need to describe it as either vertically or horizontally simple. Okay, so let's write this in the xy plane. So in the xy plane, right, so this is what we're doing. We're finding the volume of the solid region D bounded above by this parabola and below by the xy plane. In the xy plane, what does this region R look like? Well, it looks like this. There's my region R. Okay. But again, right, and here's 2, and here's 2, and here's minus 2, and here's minus 2. Okay. What kind of region is this? Well, it is simple because it's both vertically and horizontally simple. Okay, let's write it as a vertically simple region. So let me get my red pen here. So there's top function, there's bottom function, and this is on the interval minus 2 to 2. All right, so that's me viewing it as a vertically simple region. Now, it's easy to draw that picture, but I need to actually find those functions. So what are those functions? Well, this is that describes a circle, right, of radius 2. That describes this circle, x squared plus y squared is equal to 4. What's the top function for that circle? Well, it's y equals square root of 4 minus x squared. What's the bottom function? Y equals minus square root of 4 minus x squared. So how do I describe this region? All right, so how do I describe this region as a vertically simple region? I say, well, R is the region that has its y bounded by a lower and upper function. The lower function is minus square root of 4 minus x squared. The upper function is positive square root of 4 minus x squared. And this is for x between minus 2 and 2. Okay. So there's our description of our region R. Okay. So, going back to this problem, find the volume of the solid region D bounded above by the paraboloid, below by the xy plane. Well, that volume is computed, by definition, by the double integral over the region R that we found of 4 minus x squared minus y squared dA. Okay. Now that we have R written as a vertically simple region, rewriting this integral, this is the integral from minus 2 to 2 of the integral from minus square root of 4 minus x squared to plus square root of 4 minus x squared. 4 minus x squared minus y squared dy dx. So that's the integral that I need to compute in order to find this volume. Okay. So I'll do this at the beginning of class next time. I don't have time to do it right now, but I'll do this at the beginning of class next time. And I'm going to do this to show that it's bad. It's bad and it requires some integration tricks that I said you're not typically going to have to do. So it's bad, but how do we fix it? Well, we can't fix it until we have some more machinery that we'll develop in the next couple of sections. Okay. So it turns out that while this is a perfectly valid way of describing the region, and I could have done this as a horizontally simple region too, but it wouldn't really be algebraically any nicer. It turns out that when it comes to regions that look like this, there's a much more natural way of describing it that doesn't involve coordinates x and y. You've actually already seen this example, and it's the example of polar coordinates. So polar coordinates are much more convenient for describing any kind of region that involves parts of a circle or parts of a circular disk. Okay. And we will see that this region looks complicated to describe in what are called rectangular coordinates. That's just our normal x and y coordinates. But in polar coordinates, this region is much easier than that. So does anyone know, this is the last thing I'll ask, does anyone know in polar coordinates what this region looks like? So in rectangular coordinates, in these coordinates, this region, that is in the xy plane, this region looks like a closed circular disk. What does it look like in the r theta plane? If we're talking about polar coordinates. Yep, Nathan said it. It's a rectangle. It looks like a rectangle. So in the xy plane, this looks like a closed circular disk, but in the r theta plane, this looks like a rectangle. And now you can put 2 and 2 together. And I told you that I had lied to you just a little bit before when I gave you examples of regions. And I said we were only going to be able to do integration over regions that were either vertically or horizontally simple. But then I pointed out, here's a region that's neither vertically nor horizontally simple. Okay. So then how could we possibly do an integral over it? Because this region is just a rectangle in the r theta plane. So it is actually simple in another plane. You just have to transform it. What transformations are allowed in order to do that? Well, that's a little bit more complicated, and that will be the very last thing we do, basically, in this section. Okay. Yeah, Kat, yes. So polar coordinates, we will review polar coordinates. Don't worry. So you'll have plenty of opportunities to brush up on polar coordinates, because that's one of the things we're going to do in the very next section. So anyway, that's all for today. I'll do this integral, and then I'll do a swapping the order integral at the beginning of class on Monday. And then we will move on exactly to polar coordinates. All right. So have a good weekend. Now you don't have to worry about your exam. I'll be posting your MATLAB project over the weekend with a bunch of info about it, including some MATLAB guides for those of you that haven't used MATLAB before. Just basic intro stuff. The MATLAB project itself it'll be easy. It'll be assuming that basically you've never heard of nor seen MATLAB before in your life. So anyway, I will see you all in class on Monday. So have a good weekend.